So for this graph next to it, we're going to graph the inverse. So remember for our inverse, we switch our, switch our x and our y. So x equals 2 to the y, which this is what we were doing yesterday. We were writing exponential in log form. So to write x equals 2 to the y in log form, that's equivalent to y equals log base 2 of x. So the 2, that's the base of the exponent, is the base of the log. The exponent is the number that's by itself, and what was by itself is what you're taking log of. So going back to the beginning of the chapter, so again, we don't know how to graph this. Using what we know about inverses, we know inverses switch x and y. So if this is the point -1, 1/2, it's now the point 1/2, -1. If this is the point 0, 1, it's now the point 1, 0. This is the point 1, 2, is now the point 2, 1. 2, 4 is now 4, 2. 3, 8 is now 8, 3. So that's why we were reviewing inverses. Okay. And then it also reflects. So we can kind of see just from these points and so now our asymptote is here on the y-axis. Domain is all the x values. So we see x can't be negative, can't be 0. It's all positive. So our domain is x is greater than 0. Our range is y, is how low does it go, to how high is all real numbers. And our asymptote now is x equals 0. And then our y-intercept is none, and our x-intercept is 1, 0. So we can see here, again, the graph reflects across the line y equals x. Our domain and range, we should remember, hopefully these switch, and that's why it's on here. The domain here was all real numbers, so the range here is all real numbers for the inverse. Y is greater than 0, so that means x is greater than 0. There was no x-intercept here, which means there's no y-intercept here. Any questions on that one before I move the page down? I also want to point out that both of these graphs are increasing. So to determine if a graph is increasing or decreasing, as you go from left to right, are you going up or down? So here, as I go left to right, I'm going up. Here, as I go left to right, I'm still going up. So both of those are increasing, even though they're inverses of each other. All right. So here on this next one, we have y equals -1 times 2 to the x. This, again, I can make a table and plot my points. So -1, 0, 1, 2, 3. So if I plug in 3, 2 to the third, we know is 8 times -1, I get -8. 2 squared is 4 times -1 is -4. Remember your order of operations here. You do your exponent before you multiply. 2 to the power of 1 is 2 times -1 is -2. 2 to the power of 0 is 1 times -1. 2 to the power of -1 is 1/2 times -1 is -1/2. So these are the same values, except they're the negative because that point out in front. So we can plot all of these: -1, -1/2, 0, -1, 1, -2, 2, -4, and 3, -8. And I still have an asymptote there. So I didn't label all of the individual points because I had them in the table. So here my domain, again, x values. I can plug anything in for x left and right. My range is y is less than 0. I only have negative numbers, and it's not or equal to because I have that asymptote. That asymptote is at y equals 0. And this graph is said to be decreasing. As I go from left to right, the y values are going down. They're getting smaller. Okay. So here for our inverse, this one's a little bit trickier. We still switch our x and our y. I don't know, baby. So for our inverse, we have x equals -1 times 2 to the y. Before I write it in log form, what I want to do here is divide both sides by -1. So I would have, that's equivalent to -x equals 2 to the y. Which now if I write it in log form, remember the exponent, that's what's by itself. So this is equivalent to y equals log base 2, because the 2 on the base of the exponent is 2, of -x. So if I fill in my table, remember I just switched my x and my y's, and then go ahead and plot those points. What?
When Crystal's done, can I be the calculator?
Yeah.
Why is it not going to be done?
So just by switching my X and my Y's in my table, which up on the top we also did just, I labeled them. I didn't label all the points here. But same thing, our domain and range are also going to switch. So if my domain was all real numbers, now my range is all real numbers. This is going down forever and up forever. If my range is Y is greater than 0, my domain stands for X is less than 0. Sorry, I think I said greater than. Y is less than 0, so here X is less than 0. If my asymptote was at X equals 0, now, sorry, if it was Y equals 0, now it's X equals 0. My X and my Y's are always just switching. And now if I go from left to right, I'm still going down. So this graph is also decreasing.
Hey, mommy. Hey, mommy.
Okay. This one will go a little bit quicker, I think, on this part. So here we have Y equals 5 to the X. So if I plug in 0, I'm not going to plot as many points here. If I plug in 0, I get 1. So this is the point 0, 1. If I plug in 1, I get 5. And we know it's exponential, so we know the overall shape. We know it has this asymptote down here, and we know it curves up like that. So again, on these exponentials, my domain is all real numbers. Here my range is Y is greater than 0 because my asymptote is at Y equals 0. So again, for my inverse, I switch my X and my Y, X equals 5 to the Y, and then I write this in log form, which gives us the Y by itself, log base 5 of X. Make sure for your base that you're kind of putting it down below, kind of the opposite of that exponent. So 0, 1 becomes 1, 0. And 1, 5 becomes 5, 1. So here the domain is X is greater than 0 and the range is all real numbers. So my asymptote is at X equals 0. The reason we put this one on here is to show you how the base changes the graph. So I'm gonna flip it real quick. This is what it looked like when we had log base 2. And now you can see with log base 5, let's see if I can get them next to each other. You can see that this with is flatter. So flatter than Y equals log base 2 of X. This one goes up quicker, and this one's gonna be more flat. Because with our exponential, this one went up quicker, so it's closer to the y-axis here. So this one's closer to the x-axis. So just to kind of compare. So as that, if the base, you know, were 10, it would be even closer to this x-axis. It's still increasing, but it just takes longer. Here when, if our multiplier is between 0 and 1, then our graph is decreasing. So maybe you remember that from Math 1, maybe you remember that from earlier in the chapter, but kind of helping us make a table here. I'm switching, I'm going from -3 to +1. And you're welcome to use your calculator here. We know if I plug in +1, I get 1/2. 1/2 to the power of 1. If I plug in 0, 1/2 to the power of 0 we know is 1. But just kind of showing you, so 1/2 to the power of -3. Oops, sorry. Make sure if you use your calculators, you put the 1/2 in parentheses or make it a 0.5. This gives us 8. The reason it gives us 8, so 1/2 to the power of -3, remember the negative exponent flips it. So this is equivalent to 2/1 to the 3rd power. So when I plug in -2, same idea, we're going to get 4. If I plug in -1, we're going to get 2. So -3, 8, -2, 4, -1, 2, 0, 1, 1, 1/2. It still has a domain of all real numbers and a range of y is greater than 0. It's just decreasing now because our multiplier is between 0 and 1. If I fill in my table, I'm multiplying by 1/2 or dividing by 2. And then our inverse here, x equals y to the 1, just kidding. X equals 1/2 to the y. I wrote that backwards. So that's y equals log base 1/2 of x. And we're just going to flip these points. I'm not going to make a table. Hopefully we're seeing the pattern. So -3, 8 becomes 8, -3. -2, 4 becomes 4, -2. -1, 2 becomes 2, -1. 0, 1 is 1, 0, and 1/2, 1. That didn't come out as nice. That's okay. And then following the same pattern, the domain is x is greater than 0 with the asymptote at x equals 0, and the range is all real numbers. And remember, with all of these graphs, if I folded it on this line y equals x, right down this diagonal line here, that's how it's going to mirror onto itself. Or it won't be onto itself, but that's how it would reflect or mirror over that line. Some of them I think are harder to see, like these ones when it's decreasing, but it's that same idea that it flips over that line. Are there any questions before we do move on? Okay, so for 5-86, there's one more graph back here. I will end up putting part of 87 on in just a minute. So if you have that extra graph, and if not, it'll be in your notebook, that's fine. So we're gonna look at just using the log button on our calculator. Yesterday, I did show you how to type in the log base on your calculator, but our goal, so on 86, it's f of x equals just log of x, and there's no base given. So what we need to do is we need to figure out in our calculator what the base is when log is just log. So they give us a table to fill in. And they switch because they give us some y values and some x values. So again, this is straight out of the book. If you're following along, it says copy and complete the table. So they give us from -6 to 0 for y's that they want us to fill in, and 1 to 6 for x's. So we can fill in these first one, these positive x values, pretty easily, just by using the log button on our calculator. So log of 1 is 0. Log of 2 We're going to round these, is 0.30. Log of 3 is 0.48. Log of 4 is 0.60. Log of 5 is, sorry, my paper got twisted. If we're rounding that, and I was using 2 decimal places, that would be 0.70. Log of 6 is 0.78. So again, those ones we can do just by using our calculator. We can't write the inverse of this to work backwards on the other ones until we know what the base is. I wrote 0 twice here. You can wipe that one out. It's going to be the same thing. That would be 1, 0. Sorry. So we need to kind of figure out what the base is when we're just using log. So what I want you to do, if you should have your calculator nearby, and I think most of you probably have your phone nearby, and it will even have a log on it if you turn your phone. But we want to figure out what the base is on this log button. So we can just keep going. And I see that when I get to log of 10, I get 1. I'm not going to fill everything in, but I'm going to put 1 here. Remember what logs are doing. You're asking yourself, so I'm just going to kind of fill this in. This is the same. We're trying to figure out what the base is when it's not written. When it just says log, it's implied that we know what the base is. I'm just going to call it B for base. If I write this in exponential form, I actually want to write this as y equals, so it's a little less confusing too. So if I'm graphing y equals log base b of x, we know that's equivalent to x equals b to the y power. Just switching my x and my y's, or sorry, the base here becomes the base. See, what was by itself is the exponent. So we're trying to figure out what the base is here when it's not given to us. It's just the log button. So if I take this 0.101 and plug it in, remember this is x and this is y, I have 10 equals b to the power of 1. This tells us that our base is 10. So anytime you hit just the log button on your calculator, it's a base of 10. It's implied that you know that the base is 10. Hopefully that makes sense using this point that I just kind of, again, I went through my calculator and I figured out when I got to 1, and then I just wrote it this way. So the log button, log has a base of 10. And if we wanted to work backwards to fill in this table, we can use this same idea here. We're trying to find x. So here, I don't want to get too in the way. So here, if we have -6, so I'm using this equation, x equals b to the y, and we know b is 10. We have x equals 10 to the -6. This is x equals 10 to the -5, 10 to the -4, 10 to the -3, 10 to the -2, 10 to the -1. That's for that guy. So 10 to the power of -1, which hopefully we remember, but just to show you, it's that negative exponent again, will give you 0.1. 10 to the power of -2 is 0.01. 10 to the power of -3 is 0.001. It's essentially dividing by another 10 up here, which adds another 0. I didn't make my boxes quite big enough here. So 10 to the -6 is equivalent to 0.000001. So this is really the big idea from this problem. It wants us to graph it. We've graphed a lot of these today. We know a log graph, again, it's just a base of 10. So it would look very similar to this graph, except it's going to be flatter because the base is even bigger. However, kind of moving forward here, they want us to think about all of our parent graphs, the A, H, and K. We can write this the same exact way. So y equals A times log of x minus h plus k. And it's going to do all of the same things. A is the stretch factor. H is going to move it left or right. And K is going to move our log graphs up or down. Okay, so I'm gonna kind of abbreviate problem 87, but before I do that, I wanna show you a log graph on your graphing calculators and give you kind of a warning. So if I just on my graphing calculator type in y equals log of x, that's what we just did on this problem. We know the overall shape of this log graph. Again, we know it's something kind of like that. But when I hit graph on my calculator, it looks more like a square root graph. It shows more like an endpoint. Your graphing calculator doesn't draw the asymptotes correctly. So if you're using a graphing calculator when you do like your test and quizzes, or even your homework, not sure why this isn't focusing. You want to be careful that you don't make it an endpoint. You want to make sure you draw your asymptote in. Every log graph has an asymptote. The calculator just doesn't draw these vertical asymptotes for you. So I wanted to point that out. And then this last one here that we're going to do for problem 87, I'm just going to kind of use an example. So I'm going to graph y equals log base 2 of x. We already did this, and you can flip it over the page if you need to. It goes through 1, 0, and then 2, 1, 4, 2, and 8, 3. So this is the graph of just y equals log base 2 of x. We already did that one, but I'm putting it on here so that we can see the transformations. So I'm going to use a different color here. Y equals 3 plus log base 2 of x plus 4. With these log graphs, your k value is often put at the front. Not always, but this is the same as log base 2 of x plus 4 in parentheses with a plus 3 after. But they're often going to be written with that k value out in front. This 3 is not an a because it has a plus sign right here. So in this problem, this is our k, and this is our h, which it's easy to see when it's written this way, but again, this is how you may see it in some of your homework problems. So my h here is -4. So this means it goes left 4, and if k is 3, it goes up 3. So this point right here, and that's kind of like our locator point. All of these go through the point 1, 0. If I go left 4, 1, 2, 3, 4, and up 3, that's going to be that point right there. This whole graph is shifting left 4. So if this asymptote is there, 1, 2, 3, 4, this is my new asymptote here. At x equals -4. So every single one of these points just moves left 4 and up 3. Last problem, baby. So if you're given a problem like this to graph, it may be helpful to graph kind of the parent graph there. And this works with any base. And then just shift it, the h and the k. All right. So what you're walking away with today is a few things. The log button on your calculator has a base of 10. The a, h, and k do the same things for any base here. And then we also reviewed kind of what we started with is that the log graph is the inverse of the exponential just by flipping over that line. But we see what all of these log graphs look like, and they have a vertical asymptote instead of a horizontal asymptote like the exponentials. So your homework tonight is 89 to 95, skipping problem 93. You have some stuff on logs in there. Please bring your questions tomorrow. Tomorrow, just a heads up, we are doing a team test. So the expectation is that you will have your cameras on so that you can be collaborating in your groups, in your breakout rooms, and you have a test a week from today. We'll talk more about that later, but just giving you a heads up, next Tuesday during class is your Chapter 5 test. You guys are free to go unless you have questions. I will be sticking around. Otherwise, I will see you tomorrow with your cameras on at 10 a.m.